here we have f of x is x squared for x less than 1 and ax plus b for x at least 1, and we want to figure out what the values of the constants a and b should be so that f is differentiable. And this is a very common problem in college calculus when piecewise defined functions are differentiable when the pieces match or continuous when the pieces match. And this problem was actually recommended to me by a subscriber. I wanted to support them. I thought it was a cool problem. And I've taught numerous problems at Princeton University that are very similar to this. And I'm going to give you a complete mastery in this video. So let's look at this function. We want to figure out why it's differentiable. The first thing is, thinking about intuitively differentiable functions and continuous functions, I like to say that a function is continuous if you can draw its graph with a single stroke of the pen, and it's differentiable if you can draw its graph without stopping. So for example, in something like this where you have to change direction, you're stopping at this point, and this is a point where it's not differentiable. So the first thing is differentiable functions are always continuous. If you can draw the graph without stopping, you can certainly draw it with a single stroke of the pen. But that's not a formal proof, that's just an intuition. So the first step we have to think about here is the pieces are matching at the point 1. Is the function continuous at 1? So f is continuous at x equals to 1, that's a given, because we want to find out when f is differentiable. So we know that it's continuous everywhere except possibly at 1, right? The functions ax plus b and x squared are simple enough. So at x equals to 1, we're looking at the left-hand limit and the right-hand limit. That's what we're interested in. So the left-hand limit as x approaches 1 from the left of f of x is, in this case, x is less than 1. So you're thinking about the function x squared when x is less than 1. And so you're going to get basically the limit as x approaches 1 from the left, which is the same as the general limit of x squared, which is just going to be 1. Okay, 1 squared is equal to 1. You can plug in, it's a continuous function. X squared is a continuous function. Now similarly, we can do the limit as x approaches 1 from the right of f of x, and that's going to be the limit of ax plus b, because that is what f of x is when x is greater than 1. So the limit as x approaches 1 from the right of ax plus b, and that's just going to equal to a plus b. You just plug in x equals to 1. So the first equation that we have, just knowing that f is continuous, we're going to get two equations in a and b and solve for a and b. Okay, two linear equations in a and b, simultaneous equations. So here we get that a plus b has to equal to 1 because f is continuous at x equals to 1. Okay, so that's number 1. So we can write that down here. A plus b has to equal to 1. And now the next step is to show that because it's differentiable at 1, what information that gives about a and b. So that's going to give us another equation relating a and b. We're going to compute the left-hand and right-hand derivatives. We want to check that the slopes match at 1. Okay, so how do we check that the slopes match at 1? Well, we sort of want to look at what is the left-hand derivative as x approaches 1 of f of x. Okay, so the definition of the derivative, the limit definition of the derivative at 1 is limit h goes to 0, f of 1 plus h minus f of 1 by h. Okay, now one thing you can do here is, because you're thinking about x squared when x is less than 1, okay, and at x equals to 1 it's also going to be x squared, right? Because we know it has to be continuous at x is equal to 1, so it's going to be 1 at x equals to 1. So the limit definition of the derivative is going to match up with the derivative of x squared at 1. Okay, we don't actually have to go through the process because we know that when x is less than 1, we just have the function x squared and we know what the derivative of x squared is. Okay, so this is a case where we can just say this is going to be equal to 2x at x equals to 1. So this notation, if you haven't seen it before, means you just evaluate the expression at x equals to 1, put a vertical line, and that's just going to equal to 2. So that is the left-hand derivative, and I'm just going to put h approaches 0 from the left, okay? And when h approaches 0 from the right, so we're taking the right-hand derivative, then you're going to be differentiating the other function. So this is f of 1 plus h minus f of 1. Again, when h is greater than 0, you're just going to get the function ax plus b. And then you know that you're going to be differentiating ax plus b at 1. That's the definition of the derivative of ax plus b at 1. So that's just going to be, how to differentiate a linear function? It's just going to be a. Okay, the constant differentiates to 0, ax differentiates to be a. So therefore, this is just going to equal to a. So because the left-hand and right-hand derivatives have to match, because f is differentiable, we know that therefore a has to equal to 2. So that is a pretty cool equation, because now we know a plus b is equal to 1. That therefore implies that a is equal to 2. And what do you have to add 2 to get 1? Negative 1. So b is equal to negative 1. A is 2 and b is -1, and those are the values where f is going to be differentiable at x equals to 1. And you can sort of even graph the function, right? I mean, that may be an extra step. I'm just going to graph it now that we've actually found it out. You can sort of see everything. You know, that's like just a sanity check to see that it is really differentiable at 1, or it really looks nice. But the question is not asking us for that. But I think it's always good to kind of ask yourself more questions. You know, you get a deeper understanding. Even if you're trying to pass an exam, if you only think about the question you're asked, you know, your brain, when you get different kinds of variations, it takes some time to get used to. So always good practice to try out different questions. So here, the graph of x squared is going to be a parabola, which is going to be at the point, is going to be the point 1, 1. And then for ax plus b, well, we know we found 2x minus 1, right? 2x minus 1. So when x is 1, 2x minus 1 is 1. And then you're just going to get this graph, which is going to match up with the graph of 2x minus 1. It's going to look something like this. So you're going to get something like this. And 2x minus 1, you know, at -1, it's going to be this. I'm just extending the graph, but of course the function isn't defined to be 2x minus 1 when x is less than 1. So you won't see that line, but I'm just showing you it is the line 2x minus 1. Okay, so this is actually going to be the graph of the function. That's going to be the graph of f of x. So thank you so much for watching. I hope you loved that video. I was trying to support a subscriber, and also it's a great question. I'm trying to help everyone who's watching my videos and my content. And I've got lots of content on my channel on calculus, so check out my videos. I've got a whole calculus playlist based on my lectures at Princeton University. I received a university-wide faculty teaching award at Princeton. I have a lot of experience teaching freshman calculus to students. I understand where they have difficulties. I've taught calculus to you know, younger people. I've taught like ideas of calculus even to my cousin who was 7 years old at the time I started teaching at calculus. So that was when I was 10 years old. So I have a lot of experience teaching high-level math, how to think about it from a basic way. And so I hope you love my videos and the content on my channel. Check it out. Got pre-calculus, calculus, proof-based math, all levels of math. I'm a research mathematician, and I'm trying to have a unique angle on my channel of how to think about math at all levels to deliver elite math education to everyone, no matter what their background, high school or college. They can learn and they can love math. And I want to support you. I hope I've supported you with this video. Wish you all the best, and I'm super excited to see you in the next video. Don't forget to subscribe if you love my content, and I hope that everything goes super well for you, and I will see you soon.